So the next type of differential equation that we might encounter are ones where the derivative is a function of y alone, so not a mixture of x and y. So in that form, dy dx is some function of y. Now, again, this is something that can easily be separated. And we turn it into something like that. The integral of dx is the y over whatever that function of y is. We can easily handle that. Effectively, they are, yet again, a first order linear differential equation, because I could rearrange and put it in that form, and that satisfies our definition of what we said a first order linear differential equation is. Let's have a look at this one. So the initial condition problem, so dy dx is some constant times y minus n, and there's our initial condition. So when x is 0, y is n plus a. Let's separate it out. I've got dy over y minus n, and then the right hand side k just times the integral of dx. Remember, on the right hand side, when I've got something like this, 0 to x dx, I can just go, well, that's going to be x. The right hand side becomes kx. Left hand side is a log function. So substituting into our log function, we'll get log of y minus n minus the log of a, which then we can put it into 1 log. Okay, undo the log, e to the power of kx is now that expression, which means y minus n is equal to ae to the kx. Again, I didn't worry about going plus or minus, because a is a constant. E could be plus, it could be minus, who knows. Moving the n over the other side, we get this. Now hopefully that looks familiar to you, because that was our growth and decay equation, you'll recall from, I think it was last year we looked at that, wasn't it? Rate of change. And remember we said, oh well, the solution to this, to p to t is equal to some constant p minus n, turns out to be p equals n plus ae to the kt, and that's where it comes from. Let's look at this one. Separate out. Now we want to make y the subject of all this. Okay, so let's play around with the algebra on that one. I'll get e to the power of 1 minus 2y as the subject first, then log both sides, and eventually there it is. Y is a half of 1 minus log some constant minus 2x. Square root of 1 minus y squared. This time when I separate it out, that's a, what's that, inverse sine or minus inverse cos, whichever you prefer. I tend to go with the positive one, so inverse sine. So inverse sine of y is x plus c. Y is the sine of x plus c. Interesting, because we know that when we differentiate sine we get cosine. But hang on, the derivative is the square root of 1 minus y squared. Well, that's all because it's in terms of y. If you were to substitute in, what would you get? You get 1 minus sine squared, which is cos squared. Square root of cos is cos, so sure enough, when you differentiate sine, you get cos. It's still consistent with what we know. That now brings us to a very specific type of differential equation, the logistic equation. There it is in all its glory. The derivative of some function of x with respect to x is equal to some function of x times 1 minus some function of x. We simplify it a little bit, it looks a lot cleaner like this. So constant times y, I mean y is a function of x, some constant times y is equal to p minus y. And that's the one we're going to be interested in looking at. So let's do the one where p is just simply 1. The initial condition is that when x is equal to 0, y is equal to a. If we just looked at the slope field for this, there it is, we can work out that basically there's 3 shapes, if you like, that we could have, depending on the value of a. So if a was less than 0, we get this orange one here. So it kind of looks hyperbolic. If it's in between 0 and 1, we get this inflecting one. It looks a bit like an inverse tan curve. It's not an inverse tan curve, but it has that shape. And if a is greater than 1, we get the blue one. But there are 2 trivial solutions as well. So those 3 possible curves are separated by 2 trivial solutions. So in fact, we'd end up with 5 possibilities for this differential equation. With this logistic equation, this top one, so the one I've got in purple, that's what's known as the carrying capacity. Because a lot of these questions have to do with populations and things like that. So when we call it the carrying capacity, we're saying, well, what's the maximum that the population could be? It's the top asymptote would be that, the carrying capacity. Let's go and solve it then and find this equation So y, 1 minus y, separate it out. We can do a little partial fractions on the left-hand side. 1 on y plus 1 on 1 minus y. Right-hand side just becomes x. We end up with the log of y over 1 minus y. Substituting into that, well, when I substitute in y, I get y on 1 minus y. But when I substitute a, I get a on 1 minus a, but it's minus that log. So we end up with this expression, the log of y, 1 minus a over a, 1 minus y. Get rid of the log. We now have e to the x. And now I'm saying, well, a e to the x will be y on 1 minus y. Just to make the algebra nicer. So all I'm really saying is, look, instead of having the absolute value of 1 minus a on a, I'm just going to put it as a. Capital A there. So it's just some constant, that constant's equal to a on 1 minus a, or the absolute value of that. Okay, let's keep going then. We want to make y the subject of all this. Okay, I've now got it. Y is a e to the x on 1 plus a e to the x. Sure, that's an answer. There are other ways of writing it. I can do things like this. I can say, well look, I'll let b equal the reciprocal of a. Why do that? Oh, well that's nice, because now it's just 1 over a function. So 1 over this exponential function, but it becomes 1 over b e to the minus x plus 1. So there's 3 possibilities. But you remember I said 5 possibilities? But that's all to do with the value of b. For some values of b, it'll be above the trivial solution. For some values of b, it'll be below the trivial solution. And for some values of b, it'll be in between the 2 trivial solutions. They want us to find any inflection points. We know the possible points of inflection will occur when the second derivative is equal to 0. So I want to differentiate y, 1 minus y, but with respect to x. It means I've got to do it implicitly. So I can differentiate this with respect to y, but then I'll multiply by dy dx. Differentiate with respect to y, write down the first, diff the second, plus write down the second, diff the first. Multiply by dy dx, but we know dy dx is y times 1 minus y, and there I have my second derivative. 3 possibilities for 0. 0, a half, or 1. We know 0 and 1 are the trivial solutions. There certainly are not inflection points there. Therefore it's got to be a half. That's the only possible inflection point. And then I can look at my slope field, and then I can confirm that, because we can see from the slope field that, yeah, it changes. There is a change there. b e to the minus x, we're still trying to work out the x coordinate. We've got the y coordinate. Remember, b e to the minus x is equal to 1. Where on earth did I pull that from? Well, we've said y is equal to a half, and then back here, y was 1 on b e to the minus x plus 1, so therefore b e to the minus x is equal to 1. Which means e to the power of x is equal to b, x is the log of b, but b was the reciprocal of capital A, and capital A we said was little a on 1 minus a, so I've got the x value now in terms of all the pronumerals they gave me. As I say, the slope field shows us that there is a change in concavity. I don't need to go and test, I've got the slope field. So yes, that is a point of inflection. Last year's HSC. So in an experiment, population of insects modelled by this differential equation, and they've given us the slope field. And the first part of the question was, explain why the graph that passes through S cannot pass through the point T. I know there's a trivial solution at P equals 2000. That would create a horizontal asymptote. Yeah, sure, that's one solution, but in the other solutions it's a horizontal asymptote. And I know it's not going to cross that horizontal asymptote, because again, looking at the slope field, there is no way that was going through the asymptote. Sketch the graph. So I'm starting at S, and I want to follow the tangent. So remember, that is the tangent at that point. So we know the curve's going there, and then it's got to sort of follow the path of the tangents and eventually go asymptotic. Here's mine. Oh, that's not too bad. Not that bumpy. But there we go. So we know we're doing something like that. Find the predicted value of the population at which the rate of growth of the population is the largest. This is where you've got to really read the question closely. What is it asking? It's saying the rate of growth is the largest. So we want to know when p to t is the largest. Well, that's p to t. And so I could find the second derivative. That will find the stationary points of the derivative. Remember, that's what we're trying to maximise. So the second derivative would equal 0. The third derivative would then confirm that it's a maximum point, not a minimum point. So p is equal to 1,000. When p is equal to 1,000. But look, the other thing I can use is I know this. The maximum rate of change must occur at the inflection point of the curve. And we know that in the logistic curve, that's always halfway between the two trivial solutions. That's what we did in that previous example. Y value ends up being half. Remember, the two trivial solutions were 0 and 1. It's always going to be halfway between. Very good.